patent I sent in this summer. It's analog matrix multiplication with some sort of adaptation for its own flaws. I will try to explain each figures in the patent. You can find everything here in my GitHub repository. Also, you find the construction files of the circuit board I try to make. Well, now it's very heavy rain outside. It's lightnings and ice coming down. Anyway, maybe I should pause this. I'll try anyway. Distracted about the heavy rainfall. I haven't seen such big ice balls falling from the sky before in my life. But now we come back to what I should talk about. The whole idea is to do analog matrix multiplication to reduce power supply, power demand for AI in general. But analog matrix multiplication is not anything for general purpose computation like training a neural network. Then you need plus the precision you have. It's only for the inference where you not need the best possible determinism. So I come up with a bold, crazy, literally flipped upside down idea where I say, okay, let's assume we do our multiplication in a standard CMOS process, in a standard transistor like 2T 1C, and instead of trying to do this in perfection, each transistor should be predictable, I instead said, alright, we accept the individual transistor and trying to do an algorithm who compensate and have the ability to know its own flaws during full operation. So the start of the inspiration of the whole idea was not to make a patent. I saw this monster 6503, who is a wonderful, beautiful art of do. They have done a retrofit of an old 80s back in the days processor who was in 8-bit in the famous C64 computer, and I thought, oh well, I should do something similar. Lots of transistors on a PCB, but I want to do something potential new and a new type of adventure. So I come up with this idea, and here I have started to put all these transistors on the board. So this is 180 times 180 millimeter size, and I will start to put all these transistors on the area and see how large it will be. And here we see the R2R ducts and so on. But we can jump to the documentation of the patent. I send this is the Swedish Patent- och registreringsverket, I sent this month, and I think November, December, then I get my judge from these patent pending people up, probably in Stockholm, in the Swedish PRV. So we start with this. We can start with this figure 1. It's translated also. The text is translated to English, and here we see this is the main matrix. Consists of transistors, and the purpose of this is not to adjust the weight. Each reverse pulse I just put in the raw weights from the LLM or other types of neural network. The raw weights unadjusted to this main matrix, and because each transistor is individual and drifting regarding temperature and so on, the output will be very low precision, very low determinism, and when you increase the size of the matrices, then you gain more electricity saving. On the other hand, you lose even further. As I understand, you lose even further in determinism output. However, my idea was to add 2 more fully analog matrices 3 and 8, and in between these I put in typical analog activation function, and I will show this also in, here we see the sigmoid schematics. I have done some LTSpice simulation as well, and these is actually the sigmoid who make it's unlinear, and then the sigmoid function number 10 looks a little bit less, other. So we are at figure 1, yes, and here we have the summation where these 2 will hopefully cancel out at least some of the bad determinism behavior of this. And the core idea is that these dotted lines is not running at the same high speed as the throughput of the payload and the inference. These lines running at full speed, but these digital controller run at much slower speed, so you don't eat up the saving you have in electricity. And the key point is that I combine MAML algorithm whose specialty is to move fast to a new situation, and that in combination with sparse short duty time of digital controlling adaptation is my idea to not eat up the electricity bill with overhead. So we jump over to the figure 2, and here we see partially the part of matrix 3, this one. And the difference here is that I intertwine these cells who have faster, instead, ideally you don't want these capacitor to leak, but that's a physical behavior of standard transistors. Instead, I put in these faster discharge rate, so I introduce a clock. So hopefully, if this works through well, then the compensate these two matrices will know its time between its own refresh pulse, and could continuously, without continuous adaptation from digital controller, but it will in full speed, hopefully, could adjust their own compensation in this summation point. That's what was my idea, that these need also an input on this of the time, so it could reach its own proprioception, known its own body, so to speak. So that's kind of a bit crazy idea, but very cool if it works. So this figure show the intertwined physicals of all the transistors. So it's intertwined thermic on the, and if you imagine an ASIC, for instance, you intertwine it. And here we have the figure, the image of, I try to explain the fresh pulse and the leakage, and this 19 is the time you put on the payload. And ideally this window 20 is the shortest possible, so you try to minimize this measurement point 20 as much as you could, and hopefully you could just take one small part of, you know, if you're really lucky, you could probably measure a small part, and then you take next refresh pulse at the same time, at the same temporal time, and gather up all the derivatives, and then you move to another place. So these diagram try to explain that. Then we have the figure 7, who explain how I may think this could work in the MAML training structure. These here you have already the digital weights, just like in standard training. Then you put in this in a so-called flight simulator in state 40, where you hidden move the physical behavior of the silicon. And why do that? Because we're dealing with the MML algorithm, whose the whole purpose of that is to strengthen the muscles of the base model to move fast between different states. So these 40 and 41 is the MAML base model training, and this is probably not where you find the best possible accuracy. No, that's not the point. The point is to train so this base model is good to move fast with few samples to another place. Then when this 40 and 41 is done, then you start to operate and jump to 42, where you remove all the hidden offsets, because I can't afford to put this silicon in a temperature chamber and slowly change the temperature, then train another run with another temperature. Instead I put it in an emulator who hopefully could emulate temperature drifting and aging and voltage dropping. And this of course will be an engineering challenge to meet the normal distribution of the normal change of the silicon. But then you jump to the real work, the payload you want to run in 42, and hopefully you run inference as much as possible, but you have ability to take a short window of measurement in different times between the refresh pulses, and hopefully it could adapt dynamically. Here I show the insertion of the important rows where I put this CPTU voltage. It's a voltage ripple who generate a ripple through the whole matrices by this Hadamard code, so you can extract the derivative at the output without using, I mean, we're dealing with analog, so you cannot do digital backpropagation. That's why I put in these Hadamard code hardware, and it was a little trick to get that with as less as possible hardware, but I come to that. Here I show the 2T1C cell. It's an partial, just I show here's the multiplication, here's the charging, and here is the weight, and here is the digital gate. This transistor is only used for charging, and it's turned on at the refresh pulse, and these do the multiplication. Here is I try to represent the math chain through the whole atomic triad, and it was a bit tricky to realize that you cannot do the standard digital backpropagation. I was forced to argue with Gemini when we try to get out the correct type of math. So the Gemini put up of course the standard digital backpropagation, but that's not correct here. And then we have as last figure 12. Here I only show the differential. So one multiplication consists of 4 transistors in real, because I introduce and that's also standard, not the Hadamard code. I'm not sure if that's standard, but these to do differential analog computation is fairly standard, I think, because then if you have differential you can push down both the noise, but moreover you can create a virtual 0 point where you have 0 in the math easily. So indeed it's more components, but I guess that's worth it. Okay, and then we have all the text, and I will not go through that. You can put it in, do whatever you want, but there was some trick here in one thing was I figure out that we cannot do the standard way of math because it doesn't work. So trying to explain it as good as I can, and I hope all this is correct in principle. So it's just to use this when it's time for implementation. And one interesting thing Gemini come up with was actually the nice thing in when I dig into this is that we have to record what line have. We go back to the standard with to here. What line of this input data have the highest value, and we snap that. We take that and go through that row to figure out the derivative of each of these. Sorry, of each of these activation functions. We need to measure to calculate the slope of these, and that was a nice trick, because if you have zero, of course, if you have zero voltage on virtual zero data here, you will not reach any output slope. You will reach only noise. So back to the schematics. That's where the funny things start. So I try to organize all this and write in the reference number correspond to the patent in this very small matrix. And of course these matrices will draw tremendous amount of more power than a digital controller, that's for sure. Also it will be slower. My aim is to run this at, we can jump at 500 kilohertz 500 kilohertz of each time step in here. That's my aim. Maybe I slow it down even further to 250 kilohertz, and so it's settled. Everything should be settled, and all the ringing should hopefully reduce to very so it fade out all the EMC. All the ringing should be when I slow down the speed. Here I show the here you can see the old-fashioned R2 DAC. Consists of standard 0402, 0.1 resistors, very cheap, and this classical shift register. So it will be funny to test that. And then I found out rather cheap. Let's see, a rather cheap ADC as well. You can jump to this endpoint ADC. I found some 12 bits ADC who was very cheap. So I will put all the project here when I continue this project, so you can download this and put in that in easy EDR if you want to do your own circuit board. Then I also put in some design documentation of some calculation and so on. Simulations, you can find some simulation as well. So I don't know where this will lead to. However, it's an exciting journey to test what this what will this lead to. Even if it failed totally, I will probably learn a lot. And I have put also 3 different audiobooks from Notebook LM, but it's kind of okay, but it sounds like it's the silver bullet of the problem. Of course, I have no measurement, there is no silver bullet, you know that. But if you imagine, you can listen to these and have a fun journey of imagination, at least. Okay, I hope that's enough, and see you when I come further.